Okay, let's go ahead and get started. So today we're on our third way to determine delta H of a reaction. So you guys should be at this point fairly comfortable with stoichiometry, right? How did we feel about calorimetry yesterday? Pretty good? Notice a lot of the homework was asking you to then determine it per mole of like one of the reactants or something. So the important part is just to read the question, underline what they're asking for, so you can go back and fix it if you don't get there. So today we're going to do the Flippy thing using heat of formation equations and heat of combustion equations. And the first thing we're going to talk about is how to write a heat of formation and a heat of combustion reaction. And then we'll do the Flippy thing, and y'all are going to find the Flippy thing super easy. Pre-AP's already done it. I think they might have done it in regular, because I know it was on the STAR test way back when, so we might have kept it in. But we'll get there, and that you'll like, because it's fun. But to get there, we have to know some definitions. And the first is the heat of formation. So heat of formation is the heat that accompanies the formation of 1 mole of a compound from its elements with all the stuff in their standard states. Okay, what do we mean by standard states? We mean 1 atm. If it's a solution, we mean 1 molar. And our free elements basically are already formed, right? So their heat of formation is 0. So remember that the delta H of free elements is 0. Elements is 0. And we'll talk about how this affects things eventually. But what I want to do is spend a minute writing some heats of formation equations with you guys. In your notes toward the end, you all have a table that kind of looks like this, right? So that table has a list of delta H's, a list of delta S's, and a list of delta G's. What those delta H's are all heat of formation values. So somebody out there formed 1 mole of every single one of these things from their elements. And when they did, this is the heat that's associated with that. So if I wanted to be a really mean teacher, I could make you write a heat of formation equation for all the delta H's on this table. But I'm not going to do that. Okay? But I do want to make sure you guys know how to write heat of formation. And I want you, when you see this number, I want you to be thinking, yeah, that's forming 1 mole of this stuff. Okay, that's what the heat is associated with. It's not just some stupid value in a table. So anybody pick a compound that looks interesting off of this table. Any one, and look at the delta H value, because I'm going to want that number. Pick one. Magnesium hydroxide. All right. What is the delta H associated with that? All right, so that's how many kilojoules per mole it takes to form 1 mole of magnesium hydroxide from its elements. So you may be asked to write a heat of formation equation. To do that, we're going to form 1 mole of magnesium hydroxide. We cannot change the 1 in that equation. Okay, so if it ends up we have fractional coefficients, so be it. That's not a problem. In this one, we're not going to. It works out easily. But if I'm adding up, what elements make this up? I'm not talking about ions. Don't be saying magnesium plus 2 plus This is from its pure state elements. What 3 elements make this up? Magnesium. And how does oxygen exist in the world? O2 and H2. So to balance this, I can't change the 1 because this heat is per mole of my product. So I need fractions, or do I? Not in this case, I don't. It's already balanced. I'm going to pick one to show you that we'll have to, we might have fractional coefficients. So let's do ammonium chloride solid. NH4Cl has a heat of formation of negative 314.43. So if I were to ask you to write a heat of formation equation for that, we're going to form 1 mole NH4Cl. So what elements make that up? N2 plus H2 plus Cl2. Now again, I can't change that 1 mole formation. So what do I have to put in front of the nitrogen? 1/2. And I'm allowed to have fractional coefficients in thermochemistry. What about hydrogen? Put a 2, and chlorine, 1/2. Okay? So does that make sense to you? All right. Want to pick one more? Anybody pick something that looks interesting? These aren't that hard. Anyone out there? You want carbon dioxide? Is that what I heard? What, Naira, what do you want? So it's, tell me the formula. Prop is 3. Did you say propene or propane? Propane. So that's C3H8. Okay. So if we're going to form 1 mole of that and get a heat of formation of propane, we're going to do C3H8. How many C's do we need? Well, I'll just write C and H2, right? How many C's? 3. How many H's? 4. So you don't always need fractional coefficients. Sometimes you don't need coefficients at all. All right, so if I ask you to write a heat of formation equation, are we good? We're forming 1 mole of a substance from its elements. And the number here is the number that's associated with that. So why are we allowed to use this number? Like, why is this number telling us something specifically about this guy? It's because what's the delta H of all the free elements? 0. So we'll talk about Big Mama on Wednesday, but remember the product minus reactant thing? Okay? So if we have the heat of this minus 0, that's why the heat of all of these reactions are equivalent to the heat of formation of the individual things because we're making it from the elements. So all the reactants are 0. It gives us a basis of comparison. So that's why the zeros, that's why this is something we call heat of formations on this table. So let's move on. We have one more definition we need to learn and need to write, and this is just as easy. Here's just a reiteration of heat of formation. Are all of these heats of formation equations? Look at them. Yes, we're forming 1 mole from elements, 1 mole from elements, 1 mole from elements, and these are all heat of formations associated with the formation of those compounds. Another thing you need to be able to write is an enthalpy or a heat of combustion equation. Enthalpy or heat of combustion. The definition of this is even simpler. All you're going to do is make sure you combust the combustion of 1 mole of a substance. Not even to its elements. You're just going to combust 1 mole. So when you're doing this, the only kicker is you have to keep your combustion mole as 1. So whatever you're combusting, you keep a 1 in front of it. So again, you could get fractional coefficients. So someone pick something you want to combust. Want to combust some alcohol or what? Methane. Okay, we're going to combust methane. So the heat of combustion, we got to keep a 1 in front of it. So we're just going to combust it. You guys know that the products are CO2 and H2O. So to balance it, I need 4 H's. So I'm going to put a 2 here. I need 1 C, 1 C. How many O's do I have? 4. So that's easy. What do we make? We need a 2 in front of that. Let's try to get, let's do let's do methanol. Let's see what that does. I don't know. It's probably going to be fine. All right. Oops. Wait. We're going to combust 1 mole of it. That's ethanol. We add O2. So again, our products are still CO2 and H2O. So how many C's do we need? 2 C's. How many H's? 6. This is still going to be easy, so we put a 3 there. And that gives us 4, 5, 6, 7 O's. So, no, what do we have over here? You don't forget this guy, right? So we only need 6 from here. So it's easier. Yeah, I'm trying to, I know one that will not work, but I want to save it because we're using it in another problem. Let's try C3H6 and see what happens. Okay, C3H6. What's that called? Does anyone know? Propene. Again, I'm just guessing it might cause us some fractional coefficients. Maybe not. So we got to keep this as 1. So we need 3 carbons and we need 6 H's. So what do we have now here? Yes. I picked one that needs a fraction. How many oxygens do we have on the right? 9. But we have them in 2s on the left, so what do we need? 9 halves. And that's allowed. So heat of formation, formation of 1 mole of a substance from its elements. Heat of combustion is just combusting 1 mole of a substance. All right? So you ready to apply this? In this problem, given the enthalpy change for the 2 reactions below, calculate the enthalpy change for the following. We can find enthalpy all sorts of ways. It's called a state function. If I were to want to go from school, WHS, to home, I can do this, right? And my displacement in the world will be a certain value, right? But I could also go to Starbucks and then go to West Bank Library and then go back to Starbucks because I forgot my phone, and then go run down here and pick up a friend, and then realize I forgot something at school because Demo needs me to get my lab book, and then come back home. Is my overall displacement different? Okay, there's different ways to do the same thing. So today with the Flippy thing, we specifically use heats of formation equations in order to find the delta H of what I call a goal equation. Look at those 2 equations. Do you see how those are heat of formation equations? Do you see how we're forming 1 mole from its elements of each of those things? So we're going to manipulate these equations to find the enthalpy change for this, which is what I call the goal. So when we start these, this is fun. I always have a good time doing this. I always just start with the first equation given. And I ask myself, okay, what does that equation contribute to find the goal that no other equation will give? What does it have that is in the goal that the other one doesn't have? CO, right? Do you see how that first equation has CO in it and the second one doesn't? So the CO for my goal has to come from there. So what I'm going to do is notice, oh, CO is a product here, but it's a reactant here. So I'm going to rewrite this first equation reversed. And I'm going to manipulate these in order to somehow get my goal equation. I'm going to end up adding them up. So if I reverse that equation, what did I do to its delta H of negative 111? I made it positive 111. And by the way, these should be per mole of reaction, all of these. All right, so got that taken care of. So now let's look at the second equation. What is it the sole source of? CO2, right. And I need 1 CO2 here, 1 CO2 here. So I'm just going to leave that equation alone. I'm just going to make sure my arrows line up. And I'm going to leave that 394 as negative because it's negative. So before you sit there and assume you did it right, you've got to add these up, clean house, and see if you get your goal, because this is our goal. So can anything cancel? This is just like cleaning house and balancing redox. Get rid of the C's. Now we have O2 on both sides. I can only have it on one side. What am I going to do? Get rid of a half, leaving me a half here. So now I can add these up and I get CO plus 1/2 O2 gives us CO2. All right, let's go ahead and add those puppies up. Excuse me. We get negative 283. Kilojoules per mole. So once we see that our goal is matched, we can do whatever we need to do to get the answer. Like if we added it, we add the 2 values or 3 values, however many they are. Easy? Any questions on this one? So this is kind of Chem 1 level. That's kind of what we did. But what we're going to do now is we're going to ramp it up a little bit. And if you look, you see how we, again, we're given heat of formation equations. So now that I have heat of formation equations, I can manipulate those to calculate something. They want us to calculate the heat of reaction for the combustion of ethane. What do I need to do? What don't I have this time that I had in the last problem? The what, Hannah? Right. But what did I call it in the last one? The goal. Do I have the thing I'm trying to find the delta H of given to me? No. So because I don't have it, I have to write it. Well, we talked about how to write combustion equations, and that's what we're going to do here. We need to create our goal. Once we create our goal, then we'll manipulate the equations the same way. So we're going to combust C2H6. We're going to add O2, and what are we going to make? CO2 plus H2O. So now to balance, we got to leave a 1 here, combusting 1 mole. So we're going to put a 2 there, and we're going to put a 3 there. How many O's do we need? 7 O's, so I need to put 7 over 2 O's. So that is my goal. So now I've got to go through these and manipulate them to make them all add up to my goal. So starting with the first equation, what does it have in it that I'm interested in? Highly interested in. C2H6, but it's a product, right? So I'm going to reverse that equation and do C2H6 goes to 2C plus 3H2. And if I flipped that equation, I'm going to change it to endothermic and go positive 84.68 kilojoules per mole. Okay, the first one is done. What does the second equation have that's of interest? CO2. Well, it's a product on both sides, but it's the only source of it. So what do I have to do to get it to match? Right. I need 2 CO2s in my goal, so I'm going to need to multiply that equation by 2. Everything in the equation multiplied by 2. So I'm going to leave it the same direction. So 2 C's plus 2 O2s makes 2 CO2s. And if I multiply the equation by 2, I better multiply the H by 2. So what do we get when we multiply negative 394 times 2? Thank you. All right. And now that final equation, anything of interest there? What's my main thing I'm looking at? H2Os, but we need 3 product H2Os. So I'm going to multiply by 3, so I get 3 H2s plus 3 halves O2 gives me 3 waters. So I'm going to take my negative 286 and multiply it by 3 as well. Negative 858 kilojoules per mole. So what I'm going to do then is to verify, don't just now add those up. I want you to make sure we got our goal. What can we cancel? 2 C's go bye-bye. What else? 3 H2s go. So I have left that needs to be taken care of is this situation here. What is 2 plus 3 halves? Isn't it 7 over 2, right? Isn't this really 4 over 2? How convenient. That works so pretty, right? 4 over 2 plus 3 over 2 is 7 over 2. So we get C2H6 plus 7 over 2 O2 gives us 2 CO2s. What's beautiful about these problems is you've got a self-check right here. If you got the right answer here to match your goal, then you know you did the manipulation correctly. So all you have to do is do the same. So here we're going to add this plus this plus this, and what do we get? And since we're adding, we round to the least number of decimal places, which is 0. So what's our answer? Negative 1561 kilojoules per mole. Okay? So that's it for this lesson. And what did you get out of it? You need to be able to write heat of formation equations. You need to be able to write heat of combustion equations. And you need to be able to manipulate, when you're given heat of formation equations, manipulate them to get a goal that either you're given or a goal that you have to write the equation for. And that equation could be combustion. It could also be formation. They might ask you to find the heat of formation of something, and you have to write it and then manipulate, just like this. Okay? All right, that's it for today. Go ahead and work on your homework.